Hi, and welcome to Module 8 of Lecture 2. It's the last module in Part 1 of Lecture 2, and it covers the third of 3 types of hypothesis test. In this case, it's covering the case of categorical independent variables and continuous dependent variables. The modal example of this is when you have a treatment and control group, where you have two different groups, and you're trying to compare behavior in one group to behavior in the other group, or some outcome in one group to an outcome in another group. To do this, we're going to use what's called a difference in means test. We start as usual by stating our research and null hypotheses. H1 is the research hypothesis, which is that the difference in the groups is meaningful. There's a real difference in the groups, and it supports whatever we'd expect to have seen from our theory. The null implied by this is that there's no difference between groups. In the case of medical treatment, it's pretty straightforward. The research hypothesis is the medicine works, the treatment works, and the group who had the treatment will have better outcomes than the group who did not have the treatment. The null would be there's no difference between the groups, which suggests the treatment didn't produce a different outcome than the control group. Our goal, as usual, is to reject the null hypothesis and eliminate the possibility that the results we saw were just due to random chance. To remind you, this is a verbatim slide from earlier, an earlier module. The idea is to compare the relationship between two different things in our data, in this case between the groups membership and the outcomes in the groups. And we're trying to compare the relationship that we saw in our data to the null, in which there's no relationship at all. So the membership in the groups doesn't affect the outcomes at all, which is the null hypothesis. And again, I won't repeat this really quickly. We want to be 95% confident in our statement. So the relationship we observe would have occurred by chance less than 5 times out of 100, then we'll reject the null hypothesis. And we say in that case that the relationship is statistically significant at the 95% confidence level. Okay. So we're going to do a couple questions in this one. What if we care if two groups have different means? So examples that we're not necessarily going to cover all of. The Democrats have different opinions on taxes than Republicans, or anything else for that matter. Do men make more money than women? We'll deal with the men and women one with some fake data at the end of this module, and we'll do a different opinion in taxes in a second. But before we get there, just to give an overview, what we're doing here is calculating a different test statistic as before. In this case, it'll again be a t statistic, just like for the correlation coefficient. This t will be a little easy to calculate, though. And it's called a difference in means test because it has two components. The numerator in this t down here in the last bullet point is simply the difference in means between the two groups. And don't be confused with the use of x instead of y. Typically, we're just doing that here because it's typical, it's normal. You could replace all these x's with y's and think about the x being the group membership and the y's being the outcomes in the groups. Here, the x's, since there's only one variable, because the group membership is just this group or that group, we're using x instead. They mean the same thing. So the numerator here is the difference in means between a variable measured in group 1 and a variable measured in group 2. And the same variable measured in group 2. The denominator is a measure of is a pooled estimate of uncertainty across both groups. We'll get to that a little bit later. Okay, so and how we do this in general? Well, let's say we're doing the example of men and women, which we'll do at the end of the module. We'll have to draw samples that involve men and women. We could do them separately, or we could draw a sample together and separate them into men and women. It doesn't really matter. The important point is you have to draw individuals who are in your groups at random. You can't select on membership in one group in a way that's correlated with membership in a different group. That'd be bad, right? So if I picked a particular woman from one group, I could not pick only her brother in the next group. That would yield correlations that we don't want in our random sampling procedure, as we discussed earlier. This is all background that's related to the first step in our 5-step method, making sure our sampling is random. Okay, so we're going to assume from now on that all of our sampling was done at random. Each person in each group, each unit in each group was chosen with equal probability. So now let's go to a concrete example. Instead of taxes, we'll talk about military preferences. So do Republicans and Democrats have different feelings towards the military? This data comes from a 2004 national election study, and the X here, the outcome variable, are feeling thermometer ratings for the military. Then two groups would be Republicans and Democrats. That's the independent variable. Our research hypothesis would be that Democrats and Republicans have different feelings on average towards the military. In other words, the mean calculated for the Republican subgroup, X bar sub R, is different from the mean calculated for the Democratic subgroup, X bar sub D. The null hypothesis is that the mean rating for the Republicans is the same as the mean rating for the Democrats. So in other words, H0 here is that X bar sub R is the same as X bar sub D. To reject the null means reject that these two things are equal and the groups are in fact different. Okay. Here are the data. I'll get back to this at the end, but you can just get a sense. It's always good to plot your data ahead of time. And here's a histogram of the data for the two different groups, feeling thermometers for Republicans and for Democrats. These are histograms, so the y-axis is the relative frequency that each individual feeling thermometer score was observed in that particular subgroup in the data. Okay, so we're going to use those to calculate descriptive stats, which are useful both for understanding our data, but also for calculating our t-statistic. So for Republicans, the mean was 87, approximately. The standard deviation, the sample standard deviation in the Republican subgroup was almost 15. And the number of individuals in that subgroup was 317. For the Democrats, it was 76, substantially lower. The deviation, however, was substantially higher, 23, and there are 327 individuals in the Democratic subgroup. So what do we do with all this? We use the difference in means test. So here again is the formula from before. We talked already about the numerator, which is the difference, the actual difference in means, one minus the other one. But we didn't talk about the pooled estimate of error. What it actually is the square root, because you're moving from variance to standard deviation, of the variance of in the first subsample, the first group, divided by the number of individuals in that group minus 1, the number of units in that group minus 1, plus the variance in the second group, divided by the number of individuals of units in that group minus 1. So basically, you're taking the variances in both groups, adding them, but you're adding them weighted by the size of the group. So bigger sized groups, right, will end up having less of a contribution to the overall pooled error than smaller sized groups will. Because the bigger the group is, the smaller the term will be corresponding to that group, and the more effective weight you put on the other group, the smaller. So, and this is a pooled estimate of error because it includes information on error from both samples. So the null hypothesis is that this t here is 0 because the null is that the two means are equal, which makes t 0. So the bigger the t we calculate over here, the more likely it is that it's different from 0 meaningfully and significantly and not due to random chance. Okay, so let's put it together with our data. The difference in means is a little less than 11. We plug in our variances, or in this case our standard deviations, into the pooled estimate for error and the number of data points. We get a pooled estimate of 1.55. We divide the difference in means by that pooled estimate, get about 7 for our statistic. What do we compare it to? Well, we could compare it to the distribution for the t-distribution critical values on that table we saw in the previous module, but we know that for data points over 100, the t is just like the normal distribution, and the normal distribution critical value for 95% is 1.96. So we're going to compare it to that directly, and what we find is that 7 is much more than 1.96, and therefore we do see a significant difference in terms of how members of each party view the military. So the groups are in fact different, because we rejected the null that they're the same. Okay. We can also write this a little differently by looking at confidence intervals. We choose a 95% confidence interval by putting the 1.96 critical value over here in the equation, and then the confidence interval is the sample mean plus or minus this critical value, around 2, times the standard deviation of that group times the square root of the number of individuals in that group. So this is the standard error for that group. So this is the equation we did back when we first looked at confidence intervals. We do that for Republicans and for Democrats. We can write the lower bound and the upper bound of each interval. And what we see is that intervals do not overlap at all. So another way of sort of getting a visual sense of whether or not these groups are different is to look at the 95% confidence intervals. If they don't overlap at all, that means we're reasonably confident that the true means lie separated from each other. So it's another way of getting at the fact that these are two different groups in terms of their preferences towards the military. Okay, now we go back to the actual data to see what's causing the difference. It's a little subtle to see on the plot. There's two things that are different. One is that the Democrats, as you saw from the higher variance in their data, tend to have more individuals with lower feeling thermometers, in addition to the same high values. And also the Republicans' scale, the density goes higher than the Democratic scale, which means there's more individuals in the Republican side who have very high values than Democrats. So that's where it's coming from. Okay. Now, to conclude this module, we're going to talk a little bit about what this means to be significant. And we're going to use some fake data to talk about different incomes of men and women. And fake data here because we're just making up some numbers. I don't have data on this at the moment. So first, let's say we have a sample size of 200, and we survey 100 men and 100 women, and we get that the difference from the hourly wages for men is 23, for women is 20, and we get these variances. We can plug them into our equation, right? So that the numerator is 23 minus 20, or 3. The denominator plugs in the variances here, and be careful, these are variances you're given, so these are already squared. So this variance of 195 is sigma 1 hat squared already. We divide by 99. We divide this by 99. We plug it in, and we get 1.472. Is that significant statistically? No, not by our standard confidence levels, because the confidence, the critical value was 1.96. 1.472 is not bigger than 1.96, so we don't get significance. But is that because there's no real difference, even though it's $3 difference? Or is that because of maybe the sample isn't big enough to show it, considering the variance in the sample? So let's say we have 4,000 data points now, 2,000 men and 2,000 women. Same variances, but now we even have a lesser hourly wage difference, only $1 difference between men and women. So the numerator here is just 1, right? 21 minus 20 is just 1. The big difference here is even though we plug in the exact same variances in the denominator, we now plug in, instead of 99, we plug in 1,999, which is obviously much, much bigger. When we do that, we get 2.25 for a t-statistic, which does exceed the critical value of 1.96. So we would say that the difference between men and women's incomes are statistically significantly different. So what about those examples? In the first case, the difference was $3, but we didn't see a difference significantly. In the second case, we had less of an absolute substantive difference, only $1, but we did see a statistically significant difference. What was the difference? The number of data points, right? We had more data in the second case, so we were more easily able to show that we had a significant difference than we were in the first case with less data, right? But there's another difference as well, right? In the first case, $3 is substantial per hour, right? So we have a substantively significant difference, but it was not quite statistically significant. In the second case, $1 is not nothing, but it's lesser. It's less of a substantively important difference, but we do see statistical significance. So these fake data were chosen to highlight that point. That we can get situations which, in one case, you have substantive differences that are meaningful, but not statistically significant. But in other cases, you get statistical significance, but not substantive differences. Okay. So that ends this. Next, we're moving to a different set of slides, part 2 of lecture 2. We're going to start moving into regression. Thank you very much.